The last invited speaker for this workshop this year is Evangelos from Georgia Tech, from Georgia Institute of Technology. And he's also doing research in controls and decision systems. And he knows a lot about autonomous racing when it comes to the combination of perception and stochastic optimal control. Because his work, I showed some pictures here, the Auto Rally car. I'm not sure if some of you read the papers. There are like 10 papers out there. It's very interesting work. And therefore, when I look at these papers, I would call him the aggressive deep driving expert, because this car is doing very aggressive deep driving. His research is theoretical and applied, and we will see what he tells us today about controlling autonomous vehicles. So, Evangelos, I make you a host, and then you can share your screen. So you're the host now, and you're able to share your screen and unmute yourself. And
okay, can you hear me now?
We can hear you loud and clearly.
Okay. Yep. Thank you very much for the invitation. Unfortunately, I could not be in person in this wonderful meeting. I am excited to see people are using model predictive control on actual hardware. And I'm also excited to see that people use deep reinforcement learning for racing. There's always an interesting debate between which approach is better and which approach will actually make it to actual hardware. And so that's a long discussion, a long debate. I just want to make a comment before I start my presentation that there's a difference when you try to get things from a simulated environment to an actual world. And so the sooner we address this gap, the more we're going to be able to steer our research into the core questions of autonomous racing. So today I just want to give you a little bit of an overview of what we have been doing, and I will just share some thoughts in terms of some of the next research directions for my group. And it is indeed the case that we have been working a lot on off-road terrestrial navigation for quite some time now, and it has been a very fun project. So my presentation may have also some math, so I'm gonna just like try to go fast over that. And so basically there are 4 parts in my presentation. The first part is just I'm going to give you a little bit of an overview of where we are right now in terms of sampling-based methods for model predictive control. The second part of this presentation is also related to one of the papers that will be presented in ICRA, and it's, I think, one of the runners for the best planning paper. It's how we can improve these types of sampling-based controllers by incorporating covariance steering algorithms. The third part of the presentation will be some ideas in terms of how I think now we should do model learning and with model predictive control. We have been working on the model learning side for quite some time, and I think we have learned many lessons. And then I'm going to just conclude with some ideas for future research. And so we have been working a lot with these sampling-based methods. We came with this idea of model predictive path and error control, which is a sampling-based controller. And there are advantages and disadvantages like any other method when it comes down to model predictive control. And I will say that you see a lot of these disadvantages when you go to the actual real hardware. And so this actual disadvantages made us think a little bit harder in terms of what type of architectures we can have in order to make MPPI to be a little bit more robust. So if one is expert in model predictive control, he or she will not be surprised that, you know, one of the things that we looked at was tube-based MPPI, which is basically an idea of having two optimizers running on almost at the same time scale. One optimizer is related to the nominal dynamics, and then you have an optimizer that handles the actual dynamics. And the key idea is that you try to grab the actual dynamics to follow the nominal dynamics, right? So the idea essentially in tube-based MPC is that you let the vehicle becoming unstable for like few time steps, and then you grab it back to the nominal system. One of the issues with a lot of these tube-based MPC architectures is that they tend to become very conservative. And the reason is because the high-level optimizer, the optimizer that deals with the nominal dynamics, is typically not aware of the capabilities of the low-level controller, or to be more precise, when it becomes aware of the capabilities of the low-level controller, it is late, because at that point already the feedback control has kicked in to try to bring the system to the close to the nominal state. And so then we thought about this idea of making the high-level MPC controller to be aware of the low-level feedback control policy. And so then we came up with this idea of robust MPPI, which tries to avoid the shortcomings of tube-based MPC in terms of becoming very conservative, but at the same time, it tries to push more on the agility side of things. And so the next two slides, I'm going to just like talk a little bit about this architecture, which I think will be important for racing applications. And I think that will become a little bit more clear in the next slides. So the key idea in robust MPPI is more like an architecture than an algorithm, is to work with an augmented representation in which when you do sampling on a representation that involves not only your nominal dynamics that start from a nominal state, but actually the nominal dynamics starting from the state that is perturbed, right? And that's something that you can observe via your sensors. So then when you do essentially optimization here, you do optimization by taking into account the underlying feedback control law, and in this representation, X star is just the nominal dynamics, and X is the actual dynamics. The difference between the two is that essentially is the nominal dynamics plus the disturbances, which you do not know, but you can observe where the vehicle is with respect to the nominal state. So notice that in the actual dynamics, you have the feedback controller incorporated in it. And that feedback controller can be another MPC controller. It can be a LQR controller. It can be a contraction metric-based controller. There are different choices. So also there is this concept of a free energy, which is something that you try to minimize. It gives you a notion of how good the cost is when you do this optimization. So one of the issues here, key issues here, is that when you propagate your nominal state forward, you want to be able to pick a state for the nominal system that is a good state, and there is another small optimization problem that has to happen, so that when you pick that nominal state, the next nominal state, you pick that next nominal state such that it is a meaningful nominal state, right? Because if you may be, what happens many times is that you may be able to, you want to track a nominal trajectory, but that nominal trajectory may also become unstable, right? So then, and I'm not talking about here cases where somebody gives you a desired trajectory, right? I think I'm not interested on this type of applications. We are talking about the case where the trajectory actually changes at every query of MPC. And so one of the issues with the robust MPPI is that you have to have a cost function, which is okay. You can do the minimization and you can pick the next best nominal state for the nominal part of RMPPI. But there are some blockers here when it comes down to whether or not this cost function is a non-stationary cost function, right? And so the nice thing with RMPPI is that you can characterize its performance, and you can essentially bring the different components inside that inequality, which tells you essentially that your performance, this look ahead performance prediction, is of the free energy of how well you're going to do. It depends on the capabilities of the low-level feedback controller, a constraint violation term, and there is a Monte Carlo error. And so a lot of the things that we are looking right now is how we can get more useful bounds than the one that we have derived so far, which is, for example, how we can incorporate in these types of bounds the cases where there is you have generalization bounds for model learning, and you want to be able to incorporate the generalization bounds on this type of inequalities that you get inside the RMPPI architecture. Some other things that we are looking right now is multimodality. And so, of course, we have applied that. We have done testing on real hardware, and this is our testing facility that we have at Georgia Tech, and that's the auto rally vehicle. That's in the case where things are fully observable. We don't really provide to the vehicle any desired trajectory. We just let the vehicle to have a desired speed, go as fast as you can, and you do not hit boundaries. So this is kind of a video. I think you might have seen that before. Yeah, and so this is also, at this point, we have our autonomy stack has matured enough. We can go out and do almost infinite labs, which is nice. It's nice to be able to repeat robotic experiments. So we get a very consistent performance. Now, of course, on the more like on the theoretical side, there are other ways to do stochastic optimization for model predictive control. We have been looking into generalized versions of stochastic optimization. MPPI can be derived from different perspectives, and people have shown that you can derive MPPI from stochastic optimization from an information theoretic perspective. So we have been looking into other forms of information theoretic measures, such as, for example, the Tsallis divergence, which is a generalization of the KL divergence. And so then what you can see basically is that you can derive all of these different types of update rules that you have, and one of them is also MPPI, and you can generalize them. And so that's a paper that we published last year in RSS, and we did a study in simulation where we saw that this new approach to sampling-based model predictive control works better than MPPI and cross-entropy method. And we have tried that with different policy parameterizations, also with unimodal, multimodal, and we use also the Stein variational inference approach. And in all of these cases, we saw in simulation that this generalization is fruitful. Now, I have to say that when you go to an actual hardware, tuning this type of algorithms is going to be challenging. And I think my experience have shown that a well-tuned MPPI algorithm is going to be hard, or RMPPI algorithm is going to be hard to beat that on an actual hardware. Also, a lot of these generalizations come with extra parameters. And so that introduces more tuning, right? So then recently, we have been also thinking about incorporating covariance steering techniques into sampling-based algorithms. And the key idea here is that when you sample every trajectory from the nonlinear dynamics, what you do is that you can get the open loop control for this nominal trajectory. And around that state trajectory and that open loop control, you can actually also compute a feedback policy that steers the covariance around that trajectory. So that covariance steering approach, it becomes almost like a convex optimization, convex optimization problem in some cases with some relaxations. But in this particular case, we have basically a covariance constraint that makes our optimization problem to be a little bit difficult in terms of whether or not we can meet the real-time requirements of MPC control. So again, the key idea here is that you sample trajectories, but on the trajectories that you sample, you also find feedback policies that will steer the covariance around each one of these trajectories. And so you have a terminal constraint, terminal covariance constraint for each one of these trajectories, which can be thought as a hyperparameter. The motivation here was to improve MPPI, at least in simulation, when it comes down to collision. And so the paper has a comparative study with MPPI, again in a simulated environment, and then what we see is that indeed that the covariance steering MPPI has higher success rate than the standard MPPI. I have to mention here that this work is in collaboration with my colleague here at Georgia Tech, Panagiotis Tsiotras, and one of his students who is the first author on this paper. So these are some very interesting ideas. I think the key blocker right now is solving these optimization problems fast enough in real time. Here we hope that we will, by using some learning approaches, we may be able to actually learn these optimization solutions and then enable them on the use them with MPPI for real-time control. Some other approaches here is, for example, you can use these covariance steering algorithms for Tube-MPPI, so you can have a high-level MPC controller like the way you want. You can pick any optimizer, and then the low-level MPC controller can be a controller that does a steering of a covariance towards your nominal trajectory. In the case of MPPI, we don't have only one trajectory, we have an entire distribution. So you can essentially use, in the low-level MPC controller, a covariance steering controller to steer the distribution towards the one provided by MPPI. That's a paper that it is accepted to ACC, and it will appear this year. So of course, we worked a lot on model learning and model adaptation, and especially when you work in off-road situations, in off-road scenarios, it's almost necessary be able to adapt your model. I would say that, this is something that I also say to my students sometimes, that if you want to be able to understand where you are, or like what's the underlying dynamics, you have to adapt, and adaptation is something that integrates information from the past to the future. Prediction, optimality comes in the sense of being predictive, right? So it's interesting when you try to put adaptive control or model learning together with model predictive control. There is the combination is not, I will say, very natural, because these tools are looking in different directions. Model predictive controllers look into the future, adaptive controllers look in the past, and they try to integrate information. And what it may happen sometimes is that the low-level fast adaptive control scheme tries to catch up with a model predictive controller that publishes trajectories very fast. And so we did some work here in the past with L1 adaptive control and MPPI, and we published a paper here. And then we also try to incorporate other model learning techniques, such as LWPR with a neural network. We expanded the ideas on pseudo rehearsal learning, and we were able to apply that to our vehicle. And so I would say that all of these methods work, but they work because you have to do a lot of tuning, a lot of fitting. But there is always this idea of the fact that these modules are actually tuned in a separate way. And so I think that the way to go in terms of model learning is to bring together model predictive control with model adaptation, and try to have one optimization problem that does both. And so we just published a paper in RSS, and we have derived a formulation of differential dynamic programming that does that. It allows you to optimize not only for your control policy, but it allows you to optimize also for unknown parameters in your model. And so you, in this particular case, you have the standard equations of differential dynamic programming. It's just that right now you have a value function parameterization and a state action value function that's going to depend to the parameters. And so in terms of applications of these types of trajectory optimization methods, you can apply these algorithms to adaptive model predictive control, right? And again, in this particular case, you have a value function that is parameterized by the unknown parameters of your model. You can actually use these methods for optimizing between different modes of the dynamics. You may have dynamics that change. In the cases of hybrid control, for example, you can use the same formulation to optimize over switching modes in your dynamics. And of course, you can use these methods for inverse optimal control. In this case, the parameters will appear in the cost function. In the paper, we have also shown we have proved the convergence of these approaches, and we have analysis with limits and theorems in terms of the conditions of the convergence. So I'm not going to show you anything right now on autonomous racing, but I just want to tell you that we are working on deploying these methods to autonomous vehicles. This is just an example that shows that you can, in an MPC formulation, you can optimize for the control variable as well as for learning parameters in your model. In this particular case, the parameters was the length link of this and the idea is that you have a cost function that is a combined cost function, You have a horizon right now from T to T MPC. It is a look ahead horizon. And then you have also a horizon that goes backwards, a time window, which you're using for the for learning the dynamics, and the whole optimization is happening within one block of differential dynamic programming. And so, yeah, you can learn the parameters pretty fast. Also, we have used that for a project that we have with NASA Langley for optimizing between different switching modes in this air taxi application. And again, this is a co-optimization problem. So we are optimizing not only for the actual control parameters here, but we are optimizing in terms of when the vehicle is going to switch between the different modes. So I think that these are algorithms that we will, of course, have in the auto rally pretty soon. And looking forward to see the performance, especially in the context of model learning, of optimizing for learning and control. And so just some of the conclusions here. Augmented importance sampling, augmented representations. It's I think give you some level of robustness. There's work to be done in terms of cases where your perceptual system changes, in the cases where there is non-stationarity in the environment, and that has to do with how you pick your next nominal state in these augmented representations. I think we have a good start with these covariance steering methods, and I think that we are going to bring them close to real time. That's one of our future research. Co-adaptation, meaning co-optimization for model learning and model predictive control. We are right now in the process of having hardware experiments, and also an interesting thing here is that you can use these methods for optimizing for linear as well as for nonlinear feedback policies, which is actually great. Another piece of work that I was not able to talk is this idea of maximum entropy differential dynamic programming. There's a paper right now in ICRA, and so we are thinking of incorporating these maximum entropy differential dynamic programming approaches inside RMPPI to avoid local minima when we do the optimization. And since a lot of people are talking about racing and simulations, this is a video that we never published actually this work. It was a racing scenario in which we just tried to race against a human. There's always an interesting question here in terms of how much of this can be done with DeepRL and how much can be done with model predictive control. In this particular scenario, we did not use DeepRL because we went directly to the hardware. So let me go back and play this video. And so there's a guy here who is controlling the first vehicle, and there's MPPI that tries to pass the vehicle and is passing the vehicle. That was an experiment that we did, I think, back in 2015-16. And I think that one of our goals is to go to our bigger facility and repeat these experiments as well. So just a last slide. A lot of people talk about competing with a human. A lot of people talk about matching the performance of a human driver. And so I think that we can learn a lot about how human drivers control these vehicles, and I'm definitely very fascinated by the underlying neurophysiology that takes place. So I just want to. This is a fascinating topic, and it's something that I believe it's important to the robotics community as well in terms of what happens really in the brain when you have drivers and they actually can perform so well. So there are certain areas in the brain that are responsible for spatial navigation, and it turns out that people who have like taxi drivers or pilots, they tend to have these areas tend to be bigger. So there are things to learn there, and I think that we can also contribute in this type of research. And so I'd like to thank my collaborators and my sponsors here for being very nice and providing all the support for our research. And I'm really happy to be part of this group and participate in the panel discussion. Thank you.